All right, well, this is kind of one of those optimization problems. Like I told you, I'm going to hand you your quiz today so you can start it. And it'll be due Tuesday since we don't have school Monday, which I think it'll give you plenty of time. But also, I wanted to give it to you today so you have a chance to look over it and see if you're just totally lost on something. So in terms of this, we're optimizing the slope of the line with the original coordinate at the origin. So you guys remember slope?
Yeah.
How? Like what? Yeah, it's kind of interesting. We've done a lot with slope in this class, but it's always been finding the derivative and just plugging in a value to find the slope at a point. So we haven't done this very, very much at all. Anyway, y1 and x1 will just have a 0 plugged in. X1 is 0, so we're just dealing with our x. But this, if we plug 0 into the function, we'll have a 16, right? Like a 16 hanging out. Otherwise, it's x squared minus x plus 16, and then minus 0, 0, and 16. Good? You don't look like you agree.
Yeah, I don't know where why did you put minus 16?
Okay, let me write it out.
This is your y1. If you plug in for your y1, 6.
So our y2, the thing on the parabola, is just the x squared minus x plus 16. And then we would do x being 0 for the second coordinate, for the second y.
Wouldn't you just
Oh, isn't it just 0?
Because it's in the origin.
It's the origin, sorry. Yes, you're right. We're not doing the slope on the parabola. Good catch. Okay, anyway, then we have just our x. And then what do we do from there? Good? I feel like the more times I hit this, the smaller this is going to get. It's just not a good thing. M prime, I haven't written that. How do we take the derivative of that kind of? Yeah, so low and then times the derivative of the upper one. What goes here? Good. Wait, I was thinking about. Well, I'll tell you that in a second. Anyway, and then high. I'll just write it without the parentheses since it's just one. And then put a bracket. Over rho squared. And then what is our goal from there?
If you expand the top and put it all together.
Yeah, we'll clean it up, definitely in this case. Minus 16. Can you guys still see it?
Not the problem anymore.
Well, no, but what I'm writing?
Yeah.
I'll zoom back in on the problem when we get there. It's because those were so big. But anyway. Okay, so what can we get rid of? We have an x squared now. 2x squared minus x squared. X's cancel, and then minus 16. Okay, what do we do with that? Yeah. So really, it's going to be just the numerator. So x equals positive or negative 4. All right, so we're looking on the interval from 1 to 8, so we don't care about the negative 4. So it's just going to work. It's a little bit okay. The slide is really weird. It's just all sorts of weird shapes. I'll just have to scroll for our answers. Sorry about that. Now it doesn't give me a scroll bar. Urgh. I'm gonna type in a number and see if that works. I've never had this happen. So all that's just so we can see the answer choices. But before we do answer this, we need to know for sure that that's what? A minimum. So can we be sure? Like, should we just assume that it's 4? Or should we know for sure that it's a minimum?
I mean, it depends on the environment. Because if this is the test, and I'm not checking anything, I'm
Just gonna go with it.
like,
I
got
agree.
4, there's a 4 in the answer.
Yep. I mean, we know this. I don't want to try to scroll that whole thing again, but what kind of graph would this look like, do you suppose? X squared minus 16 over x squared. You know, I'm just trying to think.
Wouldn't it just have a,
Isn't it just a parabola
Probably.
of some sort or something like that? But it's definitely not going to just curve or do anything like that, right? Now, it could be some kind of like a,
Like one of those.
rational function, right? But it's not going to have lots of ups and downs.
right,
So knowing that, we can be safe that it's a minimum.
Well, there's also no answer option that says there's nothing we don't know. And so it's like either 4 or
Or not, right? Good. All right, let's talk about the can problem. Did you have a chance to do it? Did you do it? Or?
I tried.
Okay. I do want you to know how to do this. Let's see if I can get, and then we'll talk about the last topic here pretty soon. Let's get a normal shaped slide going. There we go. All right. So kind of modeling our soda can as a cylinder. We know that the top and bottom is slightly different. And the question was, is the way these are designed optimizing the material used? So this takes care of the lateral surface area. It's just the circumference times the height. And then we have the two ends that we're modeling as circles, which isn't super far off. You know, the top is a circle, and then the bottom is kind of like a hemisphere or part of a sphere because it has that indentation.
You should put parentheses 2 parentheses pi r squared.
Why?
Right.
I don't
Doesn't
need
matter.
to. It doesn't matter.
Alright.
Yeah, because this says the same as that, right? That's one area, and then that's 2.
Okay, that makes sense.
It's okay either way. And then if you look on a can, the volume is 355, and I'm going to use cubic centimeters just since that's what we're using. So we're trying to figure out if it's optimized, and it would be good to kind of explore the relationship between the dimensions anyway. How? Like, what's the process? Let's let you talk through it. Dylan, what'd you do first?
Well, at first, since we don't have I kind of thought of like the soda can as like a rectangle. It's like that's what it is, right? Like it's like spread out.
The lateral side is,
Yeah.
yes.
And then, well, I don't know. We don't like. I was just trying to find like what h is, and what the height is.
Okay. And we can eventually, but in order to do that, we have to write variables in terms, like one in terms of the other, right? So, since we're minimizing surface area, because that's the material that we're making the can out of, you want that process to be run on the surface area formula. In other words, we want to take the derivative and optimize the surface area, which means we need to use the volume to write one variable in terms of the other. Okay? So Which one do you want to do?
I
Let's-
did H.
Yeah, so let's get H by itself, because this surface area formula has an R that will stay. This is simpler. I guess we could say it that way. So V over pi R squared is another expression for H. So now we can write surface area equals 2 pi R times V over pi R squared plus 2 pi R squared. And now we can take the derivative in one variable. Why are we taking the derivative?
So we can find
To find the critical point,
Right.
right? And then, okay. So I'm going to shift from SA just to A. So A prime. Well, what in here is constant that we don't have to worry about? Obviously the 2 is, but radius isn't constant. We're trying to optimize that.
volume. You can put it.
But the volume is. I'm going to leave the volume in there for now. But yes, he's right. You could substitute 355.
It's just like it's easier for me to see it as a number instead of thinking.
Okay.
That's a constant.
So I guess before we do that, we could have simplified here. In fact, maybe I'll just do that real quick. So one radius cancels the other, and the pi's cancel. Okay. So we get 2v over r, I think.
Yeah.
Okay. And then plus 2 pi r squared. You could factor out the 2. I don't think I will. So this is r to the negative 1. So when we take and 2v, remember, is a constant. So if we take the derivative of r to the negative 1, what happens?
Negative 2v over r squared.
Yeah. And then this one just dropped the 2 out. And then what do we do with that? Yeah. Okay. And then how do you propose to do that? Good. Well, that's going to put it here, and that's fine in this case. And let's change color. And then this is a constant, so we'll just treat it as that. And then divide by 4 pi, and then cube root. Everybody good on that?
I definitely did not do it right. Well, because you remember when I asked you, like, oh, do you have to put appendices?
Yeah.
Because I thought you would have to distribute the two somehow.
Wait, what part?
Well, before I took the derivative, I turned 2 pi r squared into 4 pi r squared for some reason.
So like clear back here even?
Well, like
Here?
between your second and third step, you see how you have 4 pi r?
Yes.
I put 4 pi r squared. And then when I took the derivative, I got 8 pi r.
Okay.
I don't know if I got the right answer.
Yeah, that's very interesting. Speaking of that, remind me to go back to that one we ended class with on Tuesday after we're done with this. Okay. That is weird. I wonder how you got that extra 2.
Well, I don't know. And then for the derivative of 2vr,
2vr.
like when we were up taking the derivative,
This?
yeah, I just got 2v 2b r squared, right? Like 2b over r squared.
Instead of negative?
Yeah.
Okay. It's very strange that it all worked out though.
Yeah, I don't know.
Alright, so there's an expression for r regardless of the volume, right? We have now, if we go back, we know that our surface area and our surface area is quadratic, sort of. It has this weird piece to it. Anyway, I guess what I'm saying is, can we be sure that's a minimum? We want to minimize it, right? So are we actually optimizing on the minimum side, not the maximum? You always need to be sure, right? So how could you be sure? This is a number for this problem, right? V is 355. So this is like 710, right? And so we could turn this all into just a single result. In fact, let's just do that for this. Oh, that's too big. Over 4 pi. Let me put actually 1/3 in there. 1/3. There we go. So 3.837 in terms of AP notation. Okay. No, there's no negative. Because that's a length. We don't want it to be negative.
I'm pretty sure I got this right by divine intervention. Because I put my weird equation into calculator and then found the minimum. And so I think my equation and the right one are like similar, that they have the same minimum.
Okay.
Or like a minimum at the same point.
Interesting.
Yeah.
How funny. Anyway, so here's what I want us to do with that. So here it is. H is V over pi r squared. So if we plug in what we got, V over pi, and this is going to be a little bit weird, but cube root of 2v over 4 pi, whole thing squared. Let's try simplifying this so we have h in terms of r without having it be a single number, is what I'm saying. Does that make sense? So can we? Like what happens when you do this? Square a cube.
It's 2/3.
Wait, but why shouldn't we get it in a number? Why can't we-
Well, we will. I want you to kind of understand the optimal relationship.
Oh.
Yeah. Well, it's probably kind of hard to see in this case, but with the 2/3 there. So if we get the number, let's go ahead and do that. So this is 355 in all these places. I'll help you plug it in or show you, I guess. So 355 divided by some giant mess of a thing by pi times, there we go, 355 over 4, I better put parentheses there too, 4 pi, okay, I should be using our calculator, sorry. Oh, come on, calculator. I definitely should be using it. It's all screwed up now. Two-thirds. There we go. Get out of all of that stuff. Parentheses around all of it. Okay. I must have punched it in wrong after all that.
Yeah, well, is that the 355 times 2? Because you have 2 feet over 4 pi.
Do I? Oh, shit.
You could just plug
You
this
couldn't
up.
have said that then, man? I'm just kidding. Alright. There we go. 7.67, etc. So what's the relationship between these two?
Isn't it times 2?
Yeah.
No.
It turns out that this is double that. So if our height is twice our radius, we're optimizing the use of our material, which is kind of interesting. And we didn't have to, it's not specific for this volume, but you know, if we wanted to try to simplify all this out, we could have. I just didn't want to take time to do that. So we would have found that it's twice the radius, which is cool. And in terms of measurements for the actual can, did anybody do that part? Like measure the actual can?
No, I looked it up,
Okay.
but I didn't get consistency.
I meant to bring a can, so we could do that. Because I don't think I wrote it. So you didn't find it as a consistent result when you Well, keep that one in mind, just in terms of optimizing dimensions. And then that one we were working on at the end of class the other day, you guys pointed out right at the end that I missed this derivative multiplying to get a 6 here. Do you remember this?
Oh, yeah.
Let me remind you what we were doing.
Well, because I was like, what is happening?
The rectangle inside the parabola, that was the problem. Well, anyway, it turned out that didn't make these the same. It made it actually even more different. So the x was actually root 20 thirds. I had it as 40 thirds, and then you have it as 80 thirds. So what I ended up, the reason why, is what I'm trying to say, is because I want you to think about this x for your height references this x, right? But this x is not a coordinate, it's a width, it's like 2 coordinates. So I ended up saying that it was a dimension mismatch there, is the reason. It seems like it should work out, but those two things are talking about like apples and oranges, I guess is what I'm saying. Does that make sense? Okay. And I feel like there's that stress factor that says it seems like a completely valid approach that isn't, and that gives me stress. Like when I'm going into a test, you know, like, man, I thought that was good, and it just was off a little. So, I mean, I think you just have to plan on having a problem or two that works out that way.
Yeah.
And know that it's still going to be okay.
I mean, also, if that was like a multiple choice problem, I would have seen the square root of something over 3.
Yeah, that's true. That's a good point. Well, wait. What do you, unless they put both, or what are you saying? Like you would have just picked
Yeah.
the one that had that, but if they had both, that would be trouble. I could see them doing that. All right, last topic, which is kind of a minor topic. So basically taking what we've done and sort of briefly applying it to implicit relationships. So how can we minimize, maximize an implicit function? You guys remember implicit differentiation? Okay. So it's the same idea. Maybe highlight what we're looking for. Now it's going to be if dy dx or either 0 or does not exist, then there's a critical point. Same thing if d 2y over dx squared is greater than 0, then it's concave up. If it's less than 0, it's concave down. All that's the same. So really what's changing?
It's implicit now.
Yeah, the derivative process will be a little more complicated and you just have to pay more attention. So here we have a implicitly defined function that we need to decide if it's increasing or decreasing at this point. When it tells you at a point, that's to me good news because why?
Because we won't have to find x or y.
Yeah. And typically when we're plugging in, they're getting to the calculation realm rather than the critical thinking realm, meaning it's a little simpler, right? So why don't do you guys remember natural log derivatives?
Yeah, it's right.
Good. Why don't you just do the implicit differentiation real quick? Okay, so at that point, what can we do? Anything?
Yeah, you could divide.
Yeah.
1 over 4y squared.
Good. So 8 over 4 is 2. Y over y squared is just y in the denominator. So this one does simplify a little bit. Well, I guess I should have started by asking this, but why are we taking the derivative in the first place?
To find if it's greater or positive and negative, to find if it's concave up or increasing.
Okay. What has to be true before which derivative, I guess, are you talking about? You're talking about this one, right?
Yeah.
Okay. Well, the only information we have is this point given. To know that if this derivative is positive, is that good enough to know it's increasing or decreasing in this problem? It is.
So,
It is. Yep.
because it's just the slope.
Yep. So at this point, we're good to plug in. And what are we trying to solve for? I mean, maybe it's obvious, but just say it. Yeah, so we need to get it by itself. So we get 9, and this becomes 4. So dy dx equals 9 over 4.
So we just plug in the values.
Well, okay, so yeah, you had stepped out right at that moment, but so we have basically for increasing and decreasing, remember all we need there is just the first derivative. If the first derivative is positive at that point, that means the slope is positive, which means it's increasing. So we don't need to take the second derivative or anything, we can just plug the point in at this point. Anyway, so based on that, it is what?
9 over 2. I got 9 over 9, so I don't know.
Oh, well, 2 over a half is 4, so we're going to divide by 4.
Well, okay, because when you were doing, I was just here, and then I solved for dy dx and then simplified everything before I put everything in.
Oh.
So I might have done something.
Okay. you did that, all of that up here. You solved for dyx here.
Yeah, and then
Okay.
simplify it. Well, but then if you divide, like on the second step, if you divide by 2 over y, it would be 9x squared y over 2. Right?
Yes.
When you take the derivative, do you?
But y is a half, so that'll put another 2 in the denominator.
When you take the derivative, do you multiply for the denominator, do you do 2 times 4y? Or is it 2y dx?
You're talking back here, right?
Yeah.
So it's, if you call this u, it's natural log of u, which is the derivative of that is 1 over u. So you just take that whole thing back in.
Right.
And then you do times du dx, or du times du dx, which is 1 over u, or this whole thing, times 8y dy dx. Because then you just take the derivative inside. So 2 times 4y dy dx. But if this whole thing is u, then it just gets plopped underneath the 1.
Right. Okay. I just didn't multiply it times the 4 because I thought the 4 was just by itself.
Well, what do you mean by itself?
Like it's not part of your derivative when you take the derivative of 4y squared.
So then you're if I just said what's dy dx of 4y squared, that's a constant, so the constant rule would apply.
Yeah.
So it just kind of gets brought along.
I figured out what I did wrong.
Oh, what did you do wrong?
Well, I got everything. I got 9 over 2 over 2. So I
Which
thought
would be
that would-
18, yeah.
Well, no. 9 over 2.
Are you saying like this?
Yeah.
Oh, okay.
And that's I thought the 2 would go to the top.
Gotcha. How about you?
Well, because I already saw it, so I understand.
Okay. So it's increasing because our derivative at that point is positive. So in terms of justification, we still have to say the same thing. All right. Any questions on that one now? Seem okay? 2. So now we're saying, is the curve concave up or down? How do we decide that?
Take the second derivative.
Yeah. Which one is which?
If it's positive, then it's concave up.
Yeah.
Yeah.
Okay, any special conditions on being able to do that? On being able to use that second derivative?
Doesn't it have to be a critical point, I guess?
So in this case, dy dx has to be 0, right?
Yeah.
All right, let's work through it. We have our favorite e to the garbage.
Yeah.
Before we continue, what should we check here?
Oh, for critical
to see if there's a 0 there. For dy dx. Anyway, so let's check. What's e to the 0? What does that mean?
That it's not a perfect point at 2, 0.
Can we still check if it's concave up?
Yeah.
Okay. Because, like, think of a graph where this could be concave up, but not have a 0 at dy dx. I mean, isn't that... If we go back to just like a cubic function, along all of these points, we should know that it's concave up, even though the only point dy dx is 0 is there. So did we need to do that?
No.
So are there any special conditions on just jumping right to the second derivative? Oh, I should have done it.
Yeah.
Good thing I can undo.
Right. You need to cross out chance.
I would have been mad if I had done that on my paper. Do we have to do the product rule here?
Well, because at a point, dy dx becomes
At a point,
We're at a
dy
point.
would be...
I kept dy dx on its own.
Yeah, you did that before. You are good.
Yeah, when I found dy dx, I stuck dy dx by itself and then did the derivative of that. So I ended up having to do quotient.
Yeah. So if we don't do it that way, do you think we have to do product rule there?
Probably yes.
Yeah. So which do you think is less? Let's just do it the other way, I guess, just to save some writing. By writing d squared y over dx squared, we actually did do the derivative of that, right? So just know that it's the same as doing the product rule there. Probably just a little easier. Good?
Yeah.
Thank goodness we can just plug points into this mess, right? And then dy dx here. I guess it was nice that I figured it out, because I do have to plug it in here. Dy dx at that point was, what was it, 9/4?
No, that's from the last problem. Wasn't it? Well, because if you plug in.
It was? Yeah. Yeah, that would be bad.
I think.
Never mind. I'm just going to stick it in here. 2 times -2 over, where is that? There it is, over e to the 0. 4x squared? I mean, at this point, we should just have a number.
I know from my derivative.
Where'd you get an x squared in the denominator?
Yeah, even the y over 2x. Why is it? Just don't.
It's okay. I just looked at I just plugged in a problem that we weren't even working on.
Yeah.
All right, well, this looks positive to me. It's minus and negative, so that's all we really need to know. So is this concave up or down? Sorry, this is going all over the place. So we're applying the same, the big idea, we're applying the same concepts. It's just,
You never remember how to do.
yeah, the derivatives are messier. So. How about relative max, relative min, or neither?
Well,
Let's talk about how we've done that in this unit. How have we found those?
take the derivative, you solve for 0, you take the second derivative, and plug in point where it's 0 into the second derivative, and combine if it's positive or negative.
And this one is, I kind of think of it as like it's opposite of the previous, right? Like if it's concave up, concave up, then it's a minimum. So it has to be greater than 0, but a minimum. To me, those are kind of backwards.
Yeah.
I mean, it makes sense, but just looking directly at it, it makes it look backwards. Okay, so this is the one where, you could, by the way, also do what? If you wanted. How else have we found relative extrema?
Oh, the table.
Yeah, the table. I wouldn't probably want to do that here, but you could, right? So with that said, what has to be true? Like you talked us through getting down to f double prime, but in order to use that was called the second derivative test. What has to be true? But we have to actually be more specific. It can't just be a critical point. It has to be a specific version of finding the critical point.
It has to be 0.
Yeah. In other words, if it doesn't exist, then this doesn't work. So it has to be the 0 version. So we need this one. We do need to check if the first derivative is 0 at the point before we go on to use the second derivative. And since it's all given, what are we going to do? Yeah, just plug numbers in.
This kind of feels like a gimme question. I think we're going to plug in 0 and 1. It's not going to be 0. Then you use
E or D? What did you say?
it. Well, like.
Oh, neither. Sorry, you said neither.
Because, like, it has the word neither. Like, whenever I see, like, none of the above on an answer,
You feel like it's
you know,
that?
I'm going to think back to the none of the above.
This is funny. I feel like you should just give us a clinic for like a week before the test.
No, like literally, because it's like that makes sense. Like it saves you so much time because like there's so many questions and it's like realistically you're probably not gonna get all of them right. So it's like
True.
Right. So might as well give you
Yeah, and
shot at guessing.
It's hard because I don't know how you guys are, but sometimes when you get into those tests, I think it is just like do what you can to get the best score you can, realistically. I go into those as I want to work every problem out and get every problem right if I can, and like,
Right.
you know, and then it's stressful, and then you end up wasting too much time on a problem, and then you're stressed on another. There is probably a realistic element of just the minimum I want is a 3, but if I could get a 5, that'd be great. But you know, like
Yeah.
with some test strategy. How are you? Do you know?
failed the test.
But do you think going in, do you think you were like, I'm gonna work every problem out and mainly focus on?
I thought I did really good.
Yeah. See, I'm that way. Like I'm gonna focus on the calculus and not on the test strategies as much.
Yeah, well, that me too. Like I want to like go into every question and want to solve it.
Sure.
But I have a very low threshold until the point where I give up. Like even like when I'm like, oh, I don't know, and then I'll just guess.
Yeah, I've started to kind of realize that you're kind of always thinking test strategy,
Because like
which is good. Huh. So you would just,
like,
if this was multiple choice, you would
Yeah.
just pick neither?
if it was multiple choice, no, I would plug in 0 and 1 to dy dx,
Okay.
and then
And at least see if it's.
yeah, well, like go through the problem.
Yeah.
But then once it's like starting to get hard, I'll be like, no. and
Okay.
then just-
Do you flag them? Like, let's say you do that and it leaves you with 6 or 7 extra minutes or 10 minutes.
Yeah, so what I do is, on a question that I'm 110% sure is right, I don't mark anything on it. And then on a question that I had to guess, but it was like in between 2 guesses, or like my answer was like really close, I'll put like a little line next to it. And then on questions that like I totally guessed, I put 2 lines, and then so I go through the ones that I totally guessed on, and try to do them again. And then like the ones that I kind of guessed on, I'll just like look over my math again.
Okay.
Just to, like,
Because you have math to look at.
Mhm.
And then, so remember this time, it's all going to be digital marks. So you won't be able to do your 1 or 2 line strategy.
Well, we'll also have a scratch sheet of paper somewhere.
Yeah, that's true.
Right,
So you
each
can mark it
number.
there. That's good. Okay. This is good stuff, guys. I mean, I'll have some strategies for you, but it's good to hear from someone like you, too, right? Well, let's look into this one. So is dy dx 0? Remember, we can show in this Leibniz notation, we can show evaluating this at 0, 1, kind of like this.
No line next to it.
I tend to. I've seen it without it. I don't think it's wrong either way.
That's what city taught us.
Yeah, that's how I learned it.
It definitely is 0 because it has 2 times 0 on top.
Yeah. I'm gonna write it out just for posting sake, but
So I mean, I have to do math.
too bad you're not gonna get away with this one.
Some of the tricky meters.
My son told me that one of his teachers just recently, my gosh, this would mess with me. Gave him a test where 8 answers in a row were B.
Oh no.
Were all the same.
I saw this thing where like the answer questions, like the answers, like they had to fill in the bubbles, and it was like a pattern.
Oh my gosh.
Like the whole test, and then he was like, "Oh my gosh, this can't be right."
Yeah. I definitely tried not to do that to my students, but
Like when you get like 8 A's in a row, you're like, "No, I gotta go back."
yeah. Yeah, that's what it was. And it was 8 B's in a row, and it was all correct. They were all fine. Wouldn't that be annoying?
That messed with you so much.
Yeah.
Wow.
He said it messed with him, but he stuck with it because he was pretty sure, and it turned out to be right.
That's hilarious.
One of my calculus classes in high school or in college
I get to the math on how likely that is.
he did true and false on his question. Like not the whole test, but a section of true and false. Man, I struggled on those. I hated them because I just always overthought them. I guess you could argue that maybe that meant I didn't know it, but I don't. I think I knew it. I just talked myself out of answers. I didn't like it. All right, what are we looking for once we plug all this stuff in?
Forgot to just
Lost this thing of this.
Sorry, what? Yeah. I should write that just for notation's sake later. If f double prime is greater than 0, we have a minimum, and opposite. The other way. So 2 over 2, so this becomes 1. That one's 0, so this is a minimum. No, yeah, that was me. Okay, when it says justify, what do we have to be sure to include?
Just say,
What did you say?
it's a justification.
Well, we need to be sure to include, obviously, our answer, the point where it happened, which was 0, 1. And then what did you say?
Well, do you have to include that it's twice differentiable? I don't know if you have to include that or not, or if that's included with your work that you did.
Well, but it gave us the second derivative, so.
Yeah. I don't think we do in this case need to say that.
Okay. Say because dy equals 0 is greater than 0.
I always add this at that point, but it's probably implied. Okay. Do you remember doing this? Any questions?